You should now have a good understanding of how differential heating and the Coriolis effect contribute to the patterns of atmospheric circulation. The three-celled model helps us to understand these patterns, which are illustrated here. It is important to realize that the three cells are not equal in their contributions and that atmospheric circulation is more complex than what is portrayed using this model. Take a look at this NASA visualization found using the link below. The visualization shows variations in atmospheric circulation over a year and gives a feel for the complexity. Not only does the three-celled model help us understand atmospheric circulation, it reveals the main climates of the Earth's system. For example, the greater heating at the equator causes heating of the air and high amounts of evaporation. The warm, water-filled air expands, causing the air to cool and vapor to condense. The zone at the equator where maximum heating and precipitation occur is shown by the red circle and is referred to as the Intertropical Convergence Zone, or the ITCZ. The location of the ITCZ is shown in this satellite image by the intense cloud formation at the equator. The location of the ITCZ varies as shown on this map. The position affects the global distribution of precipitation. The three-celled model also explains the location of subtropical and polar highs. These highs are formed under the ascending arm of the Hadley cell or the polar cell. As cool air sinks, it warms and results in increased evaporation. This creates very dry desert environments. These zones are indicated on this image by the red circles. Similar to a map showing monthly temperature variations that we looked at earlier, this animation shows how monthly precipitation varies across the globe. Can you pick out the ITCZ and subtropical and polar lows? Can you see how the ITC band shifts north in the northern hemisphere summer and south in the winter? Understanding what controls precipitation variations is critical to planning for climate change. Some climate phenomena are controlled by both ocean and atmospheric circulation. For example, monsoons. Monsoons are largely driven by differences in land and ocean heating. Remember, the specific heat and other factors cause oceans and other water bodies to heat more slowly than land. In North America, we have what is called the North American or Southwest monsoon. This monsoon, like others, is controlled by differences in heating. Here, the water in the Gulf of Mexico and California warms more slowly than the land in the Southwest U.S. The land heats more than the oceans, creating a low pressure over northern Mexico and the Southwest U.S. This low pressure system pulls moist air in from the cooler ocean. This leads to high amounts of precipitation in July, August, and September in places like Arizona. The map on the left shows how much of the annual precipitation is monsoonal in these regions, upwards of 60%. The next slide is from Phoenix, Arizona, and gives you a sense of the intensity of the monsoonal rains.